So let's talk first about bare wire lines. We know that bare wire lines are intrinsically vulnerable as a source of ignition for wildfires. That line may fall to the ground energized. Staying on the ground long enough, it's a high impedance fault, but it will give you enough current to ignite a wildfire. We have the possibility of that bare wire coming in contact with a tree. Tree may be dry. It may have dry material on it. It may have a low impedance. That will cause ignition. So how can we try to eliminate these wildfire ignition scenarios from bare wires? Well, the first one we're going to try to do is avoid what we call conductor clashing, when the conductors slap into each other during high winds. So what we want to do is maintain separation of those bare wires at mid-span. If we maintain the separation at mid-span, they won't be able to slap into each other. We have various manufacturers make these interphase spacers. It's basically a nice fiberglass rod. I'm showing with Hendrix insulators on either side. They're pretty darn easy to install. The one shown here as break-off torque bolts for easy installation, fiberglass rod with high-density polyethylene, insulators for end fittings, and the lengths can go from 36 inches to 120 inches, depending upon whether you're 15 kV or 25 kV or 69 or 115 or what have you. They are pretty good, and it's a viable method to avoid conductor clashing. The next thing we want to talk about is what kind of insulators we're using. We have been introducing flame retardant insulators in the last 5 or 10 years. We know that a polymer insulator will ignite if the exposure temperature exceeds its ignition temperature. We know that wildfire temps are easily 1,100 degrees Fahrenheit up to 2,000 degrees Fahrenheit and even hotter than that. And we know that HDPE ignition temp is around 650. So if we get a static wildfire, that thing's going to go on fire, right? 650 versus 2,000 degrees. Yeah, it's going to be ignited. So we don't want insulators or anything on the system to be fuel for a wildfire. If we use flame retardant insulators and we have a passing wildfire that's passing slowly, that insulator will ignite if and when it's exposed to an open flame for some number of seconds or minutes. We know that insulator, because it's FR insulated material, it will self-extinguish after the heat or flame is removed. So even if a power line is impacted by a wildfire and extreme heat flames, it will not propagate fire to any other element or area. And this is critical. We don't want to be the cause of ignition. So we're going to do everything we can to avoid that scenario. So when we look at FR insulators, we know that cross arms and poles are flammable, possibly brushes on that cross arm. Even if we're using a non-combustible cross arm and a steel pole, I still may have brush or foliage on that cross arm. If that insulator becomes ignited, we don't want flaming drips to fall on any ignitable material, either on the cross arm or on the ground. So no dripping removes concern for bringing a fire at the top of the pole, which will extinguish as soon as the wildfire passes, to ignite something on the cross arm or beneath the pole. So this is one more system hardening technique to ensure that anything that's on the top of the pole doesn't go to the ground and ignite either the pole or the ground. So that's one more belt and suspenders technique we've got here. What are the flammability standards for insulators? Well, no flammability standards exist for insulators. So we have to, as suppliers, look to UL94, which is the standard for safety of flammability of plastic materials for parts and devices and appliance testing. We also have ASTM D3801 and IEC 60695, but these three standards are essentially equivalent. So what we have done is we've gone to UL94 and evaluates flammability behavior under an open flame, which makes sense. We want to see how fire retardant they are, really. So VO, or vertical burning requirement, is the most stringent. What we do is you test and you put cotton balls located about 1/3 of a meter, a foot and a couple of inches below that burning sample. They should not ignite by flaming particles or drops. The only way to get this test done is send it to a independent testing laboratory, and we passed UL94 with flying colors. We always test on on plaques, and plaques are like a deck of cards. You put it in a test chamber, you test it, and then you make all kinds of all kinds of conclusions, and we were able to test one material versus another. Our engineers said, well, we need a test that's a little more representative of what's happening in the field. So even though there isn't a standard, we wrote our own. So again, raw material type test intended to compare different materials. We did an in-house test designed to test real-life condition using insulators rather than planks made from raw material. We used finished material. Insulator subjected to a utility torch flame directly applied to the fin. That fin is 1/8 of an inch for 30 seconds. That flame, when that flame was taken away, that flame self-extinguished in less than 5 seconds, and the melted drops from insulator self-extinguished before they hit the ground and did not ignite the cotton balls 2 feet below. Very happy with that test. We know that our affiliate in Australia also did that test to the requirements of their Public Utility Commission there. So how about undergrounding of power lines as a wildfire mitigation tool for power lines? At first glance, underground cable seems to be an excellent solution. Underground is out of sight. Underground can't throw a spark onto dry brush. It's not subject to vegetation contact. We love underground. It seems to be the best thing since sliced bread. But with our underground cable, there are a couple of drawbacks to using it for wildfire mitigation. First of all, the cost of materials for underground is 3 to 4 times the cost of covered conductor, and 5 to 10 times the cost of bare wire. And if you start looking in urban applications where you got to dig up the pavement and move materials and move other lines, it could be 10, 20, 30, 40 times the cost of an aerial system. With underground cable, we have to look at the cost of underground transformers. They're a bit elevated. We look at the potential harm to tree roots and other environmental concerns. It's kind of hard to trench a hole without digging up roots, right? We have to look at the lack of flexibility for underground cable. How long will the medium voltage network remain unchanged? What is the future loading going to be? Are we going to reconductor? And how will those changes be handled? So we have to look at underground as some capital to install underground for future, whereas we install aerial conductor for now, and we can easily add, change, or modify in the future. So the train pretty true of all aerial networks. Undergrounding is technically viable and extremely attractive option for wildfire mitigation strategy for power lines, but it's also very expensive. And the lowest cost of avoiding wildfires, improving reliability, and still allowing for flexibility in network modifications without skyrocketing future costs points to the use of aerial covered conductor. Southern California Edison studied the effectiveness of bare wire versus covered conductor versus undergrounding, and they published a couple of IEEE papers and magazine articles describing their work. They look at the relative mitigation effectiveness factor. So they said, well, if I use bare conductor, that's only 15% effective. If they reconductor using covered conductor, they said it would be 60% effective. I saw a paper from Southern California Edison published that said 60%, it was 70% effective. Underground conversion as a mitigation effectiveness factor, they said that was 1.0. We love underground cable, but it's certainly not 100% effective because other things happen, bushing failures. They did the cost per mile. So bare wire, they said 0.3 million per mile, covered 0.43 per mile, and underground 3 million per mile. And then they did a mitigation to cost ratio, which they said was the effectiveness. Bare wire was 0.5, covered conductor was 1.4, and underground was only 0.33. So the conclusions they did from studying those wildfire mitigation strategy alternatives was that covered conductor was easily the most viable, cost-effective mitigation tool. And underground conversion, although it was massively a significant mitigation strategy tool, it had a very low effectiveness mitigation to cost ratio.